Question 15, Part B. Anita opens a savings account. At the start of each month, she deposits X dollars into the savings account. At the end of each month, after interest is added into the savings account, the bank withdraws $2,500 from the savings account as a loan repayment. Let MN be the amount in the savings account after the nth withdrawal. The savings account pays interest of 4.2% per annum compounded monthly. Part 1. Show that after the second withdrawal, the amount in the savings account is given by M2 equals X times 1.0035 squared plus 1.0035 in brackets minus 2,500 times 1.0035 plus 1 in brackets. Let's start off by defining some variables. Now, firstly, the interest rate per annum is 4.2%, but the compounding is done monthly. So we need to take 4.2% and divide that by 12 to get the monthly interest rate. So 4.2% divided by 12 is 0.35% or 0.0035 in decimal. Let's define capital R as 1 plus this amount. So that's 1.0035, and this will make the process of applying percentage increase from one month to the next much easier. Now, from here on in, when I say R, I mean capital R, since the lowercase r, in fact, is not used throughout this solution. Let's define capital W as 2,500, and that represents the amount that's taken out of the account to cover the loan repayment. So that's $2,500 per month. And X is question mark, since we don't know what X is, and ultimately we will need to find that out in part 2. So let's model this financial situation. Let's consider M1. That's the amount in the account at the end of the first month. Now, Anita is going to deposit X dollars. The bank is going to increase that by 0.35%, and we do that by multiplying X by R, and then the bank is going to withdraw W dollars, which is $2,500. So M1 is equal to XR minus W. Let's consider the amount in the account at the end of the second month. So that's M2. So we take what's in the account at the end of the previous month, which is M1. Anita is going to add another X dollars. Let's enclose that in brackets because the bank is then going to add interest or increase that by 0.35%. And we're going to do that by multiplying by R again. So M1 plus X in brackets times R, and then the bank is going to withdraw another $2,500. So we're going to take away another W. But what is M1? M1 is XR minus W. So I'm going to replace M1 here with the expression that represents M1. So that's XR minus W. So we get M2 is equal to XR minus W plus X in brackets times R minus W. Now, expanding the brackets here, we get M2 is equal to XR squared minus WR plus XR minus W. Now, what I'm going to do next is I'm going to switch these two terms around. And there's a good reason for that. Later on, we're going to factorize by grouping in pairs. So I'm going to group the X's together and the W's together. So by switching these two terms around, we get M2 is equal to XR squared plus XR minus WR minus W. Notice at this point, I'm not using the numbers or the actual values, but I'm using the variables instead to do the modeling because it's actually easier to do that. Later on though, we will substitute in the known values for W and R because ultimately that's what the question is asking us to show. Now, factorizing out X from these two terms here and negative W from these two terms here, we get M2 is equal to X multiplied by R squared plus R in brackets minus W multiplied by R plus 1 in brackets. Now, at this point, we can substitute 1.0035 for R and 2,500 for W. So we get M2 is equal to X multiplied by 1.0035 squared plus 1.0035 in brackets minus 2,500 times 1.0035 plus 1 in brackets as required. Part 2. Find the value of X so that the amount in the savings account is $80,000 after the last withdrawal of the 4th year. To make the pattern that we found in Part 1 a little clearer, I'm going to find an expression for M3. But let's go back to Part 1 for a moment. We got M2 is equal to X outside of R squared plus R in brackets minus W outside of R plus 1 in brackets when expressed using the variables. Now I'm going to go back to using the variables and then later on replace the variables or substitute for the variables the known values in order to solve for X. So what I'm going to do is factorize out R in this term here. So I'm going to factorize out R here, and we're going to end up with M2 is equal to XR outside of 1 plus R in brackets minus W outside of 1 plus R. And this was the result that we got from Part 1. Now we can move on and find an expression for M3. And if M2 is this, then extending the pattern to the next month, we get M3, which is the amount in the account at the end of the 3rd month, is equal to XR outside of 1 plus R squared in brackets minus W outside of 1 plus R squared in brackets. Now notice that we have the same factor in both of these terms. So in this term here and this term here, the common factor is 1 plus R squared. So factorizing M3, we get 1 plus R squared as the common factor, and that leaves behind XR minus W, which I've grouped together here. So M3 is equal to XR minus W in brackets times 1 plus R squared in brackets. So generalizing from this, we can come up with an expression for Mn, which is the amount in the account at the end of the nth month. So we have Mn is equal to XR minus W in brackets times 1 plus R squared plus ... plus R to the power of n minus 1 in brackets. Notice that we have a geometric progression in this set of brackets here. First term 1, common ratio R, and there are n terms in this geometric progression or geometric series. We can replace this series with the sum of a geometric series formula, which is 1 minus R to the power of n over 1 minus R. Or we can write it using the division symbol or using division notation as 1 minus R to the power of n in brackets divided by 1 minus R in brackets. So this is the sum of a geometric series with n terms, common ratio R, first term 1. So Mn is equal to XR minus W in brackets times 1 minus R to the power of n in brackets divided by 1 minus R in brackets. Now we need to find X such that M48 is equal to 80,000. So at the end of the 4th year, that's equivalent to the end of the 48th month. So N is equal to 48 in this case. And we know that there's $80,000 in the account, and we want to find the value of X such that M48 is equal to 80,000. So we need to solve for X this equation here. XR minus W in brackets times 1 minus R to the power of n in brackets divided by 1 minus R in brackets is equal to 80,000. Now we can do two things here at once, which is we can move these two terms over to the other side to make XR minus W the subject. So we can multiply by 1 minus R. So this moves over, becomes times 1 minus R. And this times 1 minus R to the power of n in brackets becomes divide 1 minus R to the power of n. So XR minus W is equal to 80,000 times 1 minus R in brackets divided by 1 minus R to the power of n in brackets. Now the next thing we can do, in fact we can do two things again in one step. We can move this negative W or minus W over to the other side, becomes plus W, and here it is here. Then we're going to enclose the entire expression in brackets and then divide by R to make X the subject. So we get X is equal to 80,000 times 1 minus R in brackets divided by 1 minus R to the power of n in brackets plus W. enclose all of that in brackets, and then divide by R. Now at this stage, we can substitute the values for R and W and then evaluate the expression. So we get X is equal to 80,000 times 1 minus 1.0035 in brackets divided by 1 minus 1.0035 to the power of 48 in brackets plus 2,500, enclose all of that in brackets. So just be careful when you're typing this into your calculator that you don't make any silly mistakes. And then we divide all that by 1.0035 and we get 4,019.42497. And because it's a dollar amount, we need to round this value correct to the nearest cent. Therefore, the value of X is $4,019.42.